like I said, so these were the dynamics of ordinary head-on collision, right? I told you, if there is a common normal between two colliding units, and if the velocities of both were along the common normal, then the collision was a head-on collision. If the velocity of at least one of the two colliding units is not along the line joining their centers, that means along the common normal, then the collision is rendered oblique collision, right? Now, so in a very general sense, these were the two colliding units, and this was the line joining their centers, and this one had a velocity, say u1, making an angle alpha 1 with the line joining the two centers, and this one had a velocity u2 making an angle alpha 2 with the line joining the two centers. These were the velocities of the two colliding units just before collision. And just after collision, center C1, center C2, the velocity of this became V1, and say the velocity of this became V2, and say this is beta 1 and this is beta 2. This is the state just after collision, this is the state just before collision for two bodies colliding obliquely, oblique collision, right? Now, whatever happens in this direction belongs to collision. Whatever happens perpendicular to C1, C2 belongs to friction, right? Now, I could jolly well conserve linear momentum in this direction or any other direction that I want, right? I could conserve linear momentum, let's say along C1, C2. When I conserve linear momentum, say the mass of this is m1, the mass of this is m2. Then what's the velocity of this in this direction? u1 cos alpha 1, right? So the linear momentum in this direction, let's say the x direction, is m1 u1 cos alpha 1 plus m2 u2 cos alpha 2 is m1 v1 cos beta 1 plus m2 v2 cos beta 2. That's conserving linear momentum in this direction, right? If I had to calculate the coefficient of restitution for this collision given this data, if I had to calculate the coefficient of restitution for this collision, then again what I'll do is, I'm not bothered about velocities that are perpendicular to C1, C2. I only look at velocities that are along C1, C2, and along C1, C2 I look at relative velocity of separation divided by relative velocity of approach. So E for this situation is going to be V2 cos beta 2 minus V1 cos beta 1, this is the relative velocity of separation along the common normal, divided by relative velocity of approach along the common normal. That means u1 cos alpha 1 minus u2 cos alpha 2. The important thing is all these numbers, V2 cos beta 2, V1 cos beta 1, etc. are algebraic. In one direction positive, in the opposite direction negative in this expression. Also, if in the numerator I have taken 2 minus 1, then in the denominator I must take 1 minus 2, or vice versa. If this is 1 minus 2, this will be 2 minus 1, etc. Right? This would be the coefficient of restitution. right? In a perfectly elastic collision, E will be 1, right? Now, in this direction, these particles have velocities, right? Say, this one has a velocity u1 sine alpha 1 like this before collision, and this one has v1 sine beta 1 after collision, right? Now, the velocity of c1 before collision in this direction, velocity of c1 after collision in this direction. Now, these are directions I mentioned belong to friction. If the two colliding units are smooth, then u1 sine alpha 1 must be v1 sine beta 1, right? Similarly, the velocity of m2 in this direction before collision is going to be u2 sine alpha 2. Velocity of c2 in this direction after collision is going to be v2 sine beta 2, right? Yes or no? So, if again they are smooth, the velocity of c2 in this direction before collision and after collision will be the same. That means u2 sine alpha 2 will be equal to v2 sine beta 2 if they were smooth, right? If they were not smooth, then the velocity in this direction for c1 before and after will be different. The velocity in this direction of c2 before and after will be different if they are not smooth. But the total linear momentum in this direction will still be the same whether smooth or not. That means I can still say m1 u1 sine alpha 1 plus m2 u2 sine alpha 2 equals m1 v1 sine beta 1 plus m2 v2 sine beta 2 can still be said. In any direction, because there is no external force in any direction, you can conserve linear momentum in any direction. Friction is also an internal force, isn't it? This one exerts frictional force on this in one direction, and this will exert on this a frictional force in the opposite direction. That still is an internal force. Friction will alter the linear momentum of the constituent particles, but will not change the total linear momentum of the system. You know what I'm saying? The total linear momentum in any direction will remain preserved, whether smooth or not. But if it was smooth, then the individual momenta in the parallel direction will also remain preserved. You know what I'm saying? Got me now? Now, can I wipe this off? Suppose there were two identical spheres. Each of mass m. This is one with center C2 and say at rest. This is at rest. All right. There is another one, same mass, center C1, right? And moving in this direction with a velocity v0. Right? Now, just before collision, this is the state just before collision, right? Now, this is the common normal direction. The line joining their centers would be the common normal direction. Right? So then, this is at rest, and this has a velocity v0 inclined with the line joining the two centers. Then what's the nature of the collision? Oblique collision. It's an oblique collision. It's an oblique collision. Right? Now suppose the now suppose the collision is perfectly elastic. Now suppose the collision is perfectly elastic. Say it's a perfectly elastic collision. Okay. This is just before collision, even though I've shown this distance, this is when they are just impacting each other, right? And say this angle is theta, this angle is theta, right? Which means, say, this C2 represents one sphere, C1 represents the other sphere. This is the common normal direction. This is V0 and this is theta. So this is V0 could be resolved as V0 cos theta along the common normal direction, which causes the impact, which participates in collision. Whereas this belongs to friction, say. This is the parallel direction. Perpendicular to the line joining the centers will be the parallel direction of the common tangent direction, and this belongs to friction, V0 sin theta. This is the state, and this is at rest initially, and they are identical masses undergoing a perfectly elastic collision. They are undergoing a perfectly elastic collision. All right. Now observe that if these two units were smooth, that means there was no friction. That means there was no friction. Suppose they were smooth. Then the velocities of C1 and C2 in the parallel direction will stay preserved, right? If the two colliding units were smooth, then their velocities perpendicular to the line joining their centers will remain the same. That means after collision, just after collision, this is C1, this is C2, their velocities in this direction will remain the same. This was V0 sin theta before collision, and this was 0 before collision. It remains 0 after collision. Because they are smooth, their velocities in this direction cannot get altered. Right? That is just after collision. Now, their velocities along the line joining their centers, V0 cos theta, right? See, these are two identical masses in a state of perfectly elastic collision, and this is the head-on component of the collision. Now, the head-on component of the collision will get interchanged, right? If they are in a state of perfectly elastic collision, then for two identical masses, the result that I derived right at the very onset, I told you that their velocities along the common normal will get interchanged. Remember that? So the velocity of this in this direction will become 0, because C2 before collision had no velocity in this direction, whereas velocity of C2 in this direction will become V0 cos theta. Is it confusing? No? Right? Which means now realize that, can I just remove the clutter from here? This is the state just after collision, right? Which means now, so let me just remove the zeros, because there is no velocity in this direction. 0. That means this one moves with V0 sin theta like this. This one moves with V0 cos theta like this. That means the two colliding units are moving perpendicular to each other. Do you see that? Right? So if two identical units collide obliquely in a perfectly elastic manner, and if they are smooth, then, and if one of them is at rest, then after collision they move perpendicular to each other. This is a result sometimes used. Right? Clear? Let me know if I could wipe this off. All that I'm saying is, if there are two identical masses, where one is at rest, the other one moves and collides obliquely with this in a perfectly elastic manner, and if they are smooth, then after collision they move mutually perpendicular to each other. Right? Which is just summarizing whatever I have derived. After collision, realize that this is moving this way, this is moving that way. Right? Now, yeah, I mean, those of you who play the pool and the fool would know enough about this. It'll look really cool. Now, let me look at the following situation. We looked at a ball falling vertically down and getting rebounced, right? Now let me look at a ball, a small particle that is hitting the earth obliquely, with a velocity v naught, say. All right. Oblique incidence. This was the surface of the earth, and there was this small particle just before impacting the earth. Along this line, this is the line of impact. Right? It had a velocity v naught. Right? This is not the line of impact, this is the line of traversal. The line of impact, must understand this, the line of impact is the line which is the common normal, where the impact is felt, observed and reported. That is always along the common normal, where it's about impact. Impact is whatever takes place along the common normal. So that's referred to as the line of impact. This is only the line of velocity. The common normal for the particle and the earth is this. This is where the impact is felt. This is the common normal between the particle and the earth. This is the common normal. Right? And say it impacts obliquely, that means at an angle theta. Theta is, the earlier case was theta equal to 0 that we looked at. So now theta is not 0 and theta is not 90 degrees. Theta equal to 90 degrees would be like this. That's no impact. Right? So this is theta, not 0, not 90. Now, realize that this velocity could be resolved as, see, if this is theta, this is also theta. So this velocity just before impact could be resolved as v naught cos theta vertically, v naught cos theta vertically, and v naught sin theta horizontally. For the particle P. Now, what is the velocity along the line of impact? What is the velocity that participates in collision? V naught cos theta, right? V naught cos theta part, and V naught sin theta belongs to friction, because that rubs against the floor. So that will change if there is friction. Then V naught sin theta will change, right? So this is just before collision. Right? The particle impacts with a velocity v naught like this at an angle theta with the vertical. Right? Now, trying to get intimate with physics. Now, after collision, this is just before collision. Now, just after collision, this is the common normal direction. Right? Cn. This velocity will get multiplied by E, the coefficient of restitution. So it will rebounce in this direction with a velocity E V naught cos theta. Right? Right? Now if this surface is smooth, then this velocity after impact will remain the same. And its net velocity after impact, Vn squared is going to be V naught squared sine squared theta plus E squared V naught squared cos square theta would be its, right? This Vn squared would be this square plus this square. Yes or no? After impact? That means after impact, realize that this is the velocity diagram. Just after impact, this is Vn, this is EV naught cos theta, and this is V naught sine theta, right? And suppose this angle is beta. Then do you realize that tan beta would be V naught sine theta divided by EV naught cos theta? Which is tan theta by E, right? No? Sounds all right? Which means now, so this brings us to an important result. So if it impacts at an angle theta, it will rebounce with an angle beta. If it impacts with an angle theta with the common normal, it will rebounce with an angle beta with the common normal, such that tan beta is going to be tan theta by E, where E is the coefficient of restitution for the collision, right? So where beta is the angle of reflection, theta is the angle of incidence. In a perfectly elastic collision, E will be 1. In a perfectly elastic collision, E will be 1. Perfectly elastic collision, E is 1, or tan beta would be tan theta, or beta would be theta. It will obey laws of reflection. Angle of incidence will be equal to angle of reflection. That is what it would obey. No, please, that's not even related to this. It's just that I made a very passive reference to that. It's not. Yes, of course, you're right. It'll rebounce with this velocity, then there'll be a horizontal component, vertical component, it'll take to a projectile, regular parabolic trajectory. Yes, of course, you're right. So this is important to remember. Tan of the angle of reflection is going to be tan of the angle of incidence divided by coefficient of restitution. Clear? Can I wipe this off? Is this settled? Vertical component will become E0, so it will only float on the ground, isn't it? If it's a perfectly inelastic collision. EV naught cos theta 0 ho jayega na, so it will not move up, it will just slide on the ground. Now say no, obviously we don't apply. It is infinite because beta becomes 90 degrees, isn't it? So it is infinite, isn't it? Beta is becoming 90 degrees. Now, suppose there is a massive ring, heavy ring of radius r centered at O. There is a particle, small particle, that means whose mass is small compared to that of the ring. A small particle starts from A at this point on the circumference, and it's imparted a velocity along this line. It's imparted a velocity v naught along this line, right? And hits the ring at B. It hits the ring at B. Okay. Now in this case, the common normal direction will always be the radius at the point of impact. Huh? No, that's the common, because this is the common tangent direction. So perpendicular to it will always be the common normal direction, right? So O is the center. And suppose this angle is theta. Suppose this angle is theta. All right. Now it hits at B, then it goes to C, and then it comes back to A. Say it comes back to A. I now want to be able to find, see, at each there are two collisions, one at B and one at C, before it arrives at A, right? Now I want to be able to find, if it does this trajectory, I want to find a relationship connecting tan theta and E. Tan theta and E. Suppose I want to connect tan theta and E if it comes back to the starting point. All right, clear? Now when it's impacting at B, this is the common normal direction at B. The radius at the point of impact would be the common normal direction at B. And if this is theta, what is this? Theta here, isosceles triangle. Just because you are in class 11, you are not going to forget what you learnt in class 6 or maybe 5 or 7. Right? Isosceles triangle. So the angle of incidence is theta, right? The angle of incidence is theta. Now it goes this way, it goes this way. So this would be the angle of reflection, say beta. And if E is the coefficient of restitution, then do you realize that tan beta would be tan theta by E? Tan of the angle of reflection would be tan theta by E, a result that we arrived at a little while ago. So we have tan beta equals tan theta by E. Okay, right? Now if this is beta, this beta, नहीं ना बीटा ना, नहीं, आप मेरे को माफ कर दीजिए, नहीं यार उसके बिहाफ पे बोला या मेरे बिहाफ पे बोला? Okay, so now the new angle of incidence is beta for C, and say the angle of reflection, see it goes in this path, this is the normal at the point of incidence OC, right? Say this becomes gamma, right? Then what's the relationship between gamma and beta? Beta by E. Tan gamma is tan beta by E, where tan beta is tan theta by E. So this will, in terms of theta, it will be tan theta by E squared, right? Writing tan beta as tan theta by E, it will become tan theta by E squared tan gamma. Good. So I know beta and gamma in terms of known theta. Now for this to be a triangle, What's required? Yes, 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 absolutely. 2 theta plus 2 beta plus 2 gamma. This is gamma, so this must also be gamma. 2 theta plus 2 beta plus 2 gamma must be 180 degrees for this to be a triangle, right? So, twice theta plus beta plus gamma must be 180 degrees in order that it could come back to the starting point, right? That means theta plus beta plus gamma must be 90 degrees, or say beta plus gamma must be 90 minus theta, or tan beta plus gamma must be cot theta, taking tan of both sides, right? And then I can expand this tan beta plus tan gamma by 1 minus tan beta tan gamma. Must be cot theta. Now tan beta I can write as tan theta by E, tan gamma I can write as tan theta by E square. This then will be the required relationship, yes or no, between tan theta and E. I can cross multiply if you like, you can simplify or leave it here, does not matter, right?